dear classmates, welcome back to the fault simulation chapter. Because fault simulation is very important, we have many different simulation techniques available. In this video, we will introduce the differential fault simulation proposed by Chen in 1989. Before we discuss the differential fault simulation, we want to know what is the nature of fault simulation. Given m faults and n patterns, we actually need to simulate an m by n two-dimensional matrix. So we will need to fill in every cell in this two-dimensional matrix, where Gi represents a good circuit with test pattern Vi applied, and Bki represents the bad circuit with fault K and the pattern Vi applied. So this is actually a very difficult work to simulate the whole two-dimensional matrix. Now, as we have discussed before, PPSFP, which means parallel pattern single fault propagation. PPSFP has simulated many versions of bad circuit together. For example, suppose this is our word size W. So PPSFP would simulate W patterns in parallel for the good circuit. And then it will move on to the same W pattern of fault number 1. And then it restarts from the initial good circuit and simulate the second fault again. The problem with PPSFP is that because we cannot preserve the sequential circuit state, so PPSFP is not applicable to sequential circuits, since it does not take care of the state relationship among two neighbor patterns. Now let's discuss the concurrent fault simulation. As we have shown earlier, the concurrent fault simulation simulates one pattern at a time. It can simulate many versions of faulty circuits together with the good circuit. The advantage is that we can preserve the circuit state, so it's applicable to sequential circuits. However, as we move on to the next pattern, Vi plus 1, the concurrent fault simulation will need to store all the previous state of Bki such that we can continue to simulate Bki plus 1, so that we can simulate sequential circuit. But this is a big memory management problem because there are so many faulty circuits, so we might not have enough memory to do so. Now let's have a short quiz. Which one of the following is correct? A. PPSFP is applicable to sequential circuit. B. Concurrent fault simulation is applicable to sequential circuit. C. PPSFP wastes memory to store FF state. Have you got the answer? Yes, the answer is B. Concurrent fault simulation handles sequential circuit. PPSFP cannot handle sequential circuit because it does not store any flip-flop states. Now let's introduce the differential fault simulation proposed by Chen in 1989. The full name is called differential fault simulation, or DSIM. The idea is that we record the difference of flip-flop state from the last simulated circuit. This can be either a good circuit or a faulty circuit. This simulation technique is better than PPSFP because we only simulate one pattern at a time, so we can preserve the sequential circuit state. This technique is also better than concurrent simulation because we only record the state difference between two versions of the circuit, so we can reduce our memory consumption. According to the original paper, DSIM is up to 12 times faster than concurrent fault simulation and PPSFP. In summary, DSIM combines the merits of concurrent and the PPSFP. Now let's introduce the DSIM idea. First of all, we simulate one pattern and one circuit at a time, starting from the good circuit and the pattern VI. We simulate GI, followed by the first bad circuit B1I, and then B2I, and etc. After we finish all the bad circuits of pattern VI, we then move on to the next pattern VI plus 1. So we simulate GI plus 1 and the B1I plus 1 and so on. Remember, we always store the state difference between the previous simulated circuit and this circuit, so the storage we need is very small. So here is an animation to help you to remember the operation. Starting from GI, we move downward all the way to the bottom, and then we start the next one. So this is the operation of DSIM. In this figure, we can see that we always recover the sequential circuit state from the last simulated circuit. For example, we recover state B1I from good circuit GI, and we also recover B2I from the state of B1I. Because we only store the state difference, so we can save a lot of memory. Now let me show you some example. Given this sequential circuit with two inputs, A and B, and one flip-flop, suppose we apply two sequential patterns. AB are 1, 0, 1, 1. Suppose we also know the initial state of the flip-flop is 0. So initially, input C is 0. Let's consider two faults, A stuck at 1 fault and J stuck at 0 fault. In this example, we will not perform fault dropping for demonstration purpose. In this table, every column represents a test pattern, and the first row represents the good circuit, the second row is A stuck at 1 fault, and the third row is J stuck at 0 fault. Now let's apply the first pattern AB is equal to 1, 0 to the circuit. In this way, we know that the good output K is equal to 0. We will record this good output for the good circuit. And the next state of the flip-flop will be 1. We also record this for the good circuit. In this table, we would use blue color to represent logic value and the green color to indicate flip-flop state. Now let's inject the first fault A stuck at 1 fault into the circuit. Because this fault does not create any new event, so there is actually no event going on in this simulation. The flip-flop values is the same as the good circuit, so we do not need to store the state difference. Also, the primary output K value is the same as the good circuit, so the fault is not detected. So in this square, actually, we do not record any information. Now we move on to the second fault. First of all, we remove the A stuck at 1 fault here, and we inject a new fault J stuck at 0 here. Because we inject this fault, we create this event where J is falling to 0, so that K is rising to 1. Because the value of K is different from that of a good circuit, so this fault is detected by pattern V1. And also please note that the next state of the flip-flop would be 0, which is different from that of circuit B11. So we will need to record this state difference. So in this square, we will need to record two things. First, the fault is detected, and the state difference of flip-flop, it will be 0. Now it's time for you to work on a quiz. Suppose we want to inject a new fault, fault 3, into this circuit. Question 1. Please fill in the question marks. Question 2. What is the value of K? Is the fault detected by pattern V1? Question 3. What is the next state of flip-flop? Will this information be recorded? Please now pause the video and work on this quiz. Okay, have you finished? Now we have created a new event. This will be rising to 1, and H will be rising to 1, J will be falling to 0, and the K remains 0. So the value of K is 0, and the flip-flop future value is 0. So the fault is not detected by this pattern since it's the same as the value of the good output. Question 3. Since the value of the flip-flop is exactly the same as that of B21, so this information will not be recorded because there is no state difference between B21 and the B31. So the answer is no. Have you got it correctly? After we finish the first vector V1, now let's move on to V2. First of all, we cancel the previous fault J stuck at 0. Now we run a good circuit simulation. A is now falling to 0. As we have known from the previous simulation, we know that the next value of flip-flop will be 1. So we have 2 new events coming in, which will trigger 3 more events in the circuit. And now we know k is equal to 1 in vector 2, and the future value of flip-flop will become 0. We need to record these 2 information. Now let's move on to the first fault. We inject A stuck at 1, 4 here into the circuit, which will trigger this event and followed by this event. Since k is different from that of a good value, so we know that fault 1 is detected by this vector v2. However, the next value of flip-flop is unchanged, so we do not need to record anything about the flip-flop. Now let's move on to the second fault. First, we cancel the A stuck at 1, 4, and we inject J stuck at 0, 4. Please note that from the previous simulation, we know that the flip-flop value will be 0. So we have a C falling to 0 event, which will trigger this event. But the other values remain unchanged. K is equal to 1, which is the same as the good value. So the fault is not detected by V2. Please also note that the future value of flip-flop is still 0, which is the same as B12. Therefore, we don't need to record any state change for B22. As you can see in this table, the information we need to store for the simulation is very small. So the differential fault simulation can handle very large design with very small memory requirements. Now it's time for you to work on a quiz. Given this stuck at 1, 4, please answer these 3 questions. Now please pause the video and work on the quiz. Okay, have you finished? From the circuit B31, we know that there is no flip-flop change. So the value of C remains 0. So there is no new event here. And this is stuck at 1. So this is not change. And the K is still 1. So there is no change in K. Since K is the same value as the good circuit, so the fault is not detected. Since the future value of flip-flop is still 0, so we will not record any flip-flop change. So this square will remain blank. Have you got it correctly? Now let's show you the official differential fault simulation algorithm. For each test vector, if V1 is the first vector, we will initialize the circuit state. Else, we will remove the previous injected fault, and we would recover the current status from the previous good circuit. For example, we will recover the good circuit state of V2 from V1. And then we set the pattern Vi as primary input we run event-driven simulation. We store all the primary output. In this example, we will store the value of k. This is to compare the result with other faulty circuits. And we set the sensitized output counter to 0. This counter records the number of mismatches between faulty circuit and good circuit. And then the following loop is for the faulty circuit. For each fault in the circuit, we will remove the previously injected fault and recover the current state from the previous simulated circuit. We inject the current fault, we run event-driven simulation. If we find that the sensitized output counter is greater than 1, for example, this output is different from the good output, then we will detect the fault. In this way, we can drop the fault. In summary, in this talk, we talk about differential fault simulation. It simulates one vector at a time and one circuit at a time. Because we stored the state difference for the circuit, so we can handle sequential circuit. The advantage of differential fault simulation is that it's applicable to sequential circuits. It's better than PPSFP, and it also requires very small memory, so it's better than concurrent fault simulation. Since it's an event-driven simulator, it handles delay faults. In summary, differential fault simulation is very useful for sequential circuit in practice. Finally, we have a FFT for you. If a fault is detected, let's say B21 is dropped, how can we restore the flip-flop state of the next fault? There will be a broken chain. How can we handle this problem? Why don't we just record the flip-flop difference between the faulty circuit and the good circuit? This is a good question for you to think about. Thank you. Bye-bye.